So hello everybody and welcome to this session. We finished talking about logic and we did a few sessions on number theory before that. So today we are going to go into some branches of mathematics that involve accounting and statistics and things like that, which are closely related to fields like computer science. And this is usually, branched under discrete math, which is a very interesting branch of mathematics and extremely useful in modern day computations and things like that. So we are going to study about combinatorics and probability and maybe a little bit of graph theory if we can, because I have a couple of friends who are really good at that and they can take a couple of sessions and teach, and then we can discuss about algorithms and so on. So what we're going to talk about today, is some of the basic concepts of probability, which all of us are very aware of, and we have been studying about probability since we were 12 or 13 years old, but we will try to do problems which are a little tricky, not so simple, and we'll try to understand what this branch of mathematics actually does. So the thing about probability and statistics, which is different from number theory, which is like completely different from number theory. In fact, they're on the opposite sides of the spectrum. So in number theory, it's more to do with proofs, and it's understanding one particular concept, and you have one theorem and you have a long proof or you have some conjectures, and it's very rigorous and it is very abstract. You have to imagine a lot. You don't really see it in the world. Like, for example, we don't find the Riemann hypothesis if we look outside in the world. I mean, some people might, but it's not visible to the common man. Whereas probability and statistics and combinatorics, on the other hand, are completely to do with analyzing data and coming up with some sort of conclusions, and you make some predictions. Math is usually extremely accurate, but when we talk about probability and combinatorics, we are trying to make some sort of a guess. We are trying to make a very educated prediction about certain events. And this is actually how most of the things work. Like, for example, weather forecast or statistics in a cricket match. Like, for example, somebody walks out to bat and you say that he has a batting average of 57. That doesn't really mean that he's going to score 57 runs. It just says that because of what he has done in the last 5 years, there is a high chance that he might score 57 today, or that is how much he scores on an average, or things like that. So this is more of an intuitive branch of mathematics. There is a very, we're not going to talk too much about proofs. We're just going to try to solve some difficult problems, and we're going to try to understand the meaning behind it. So to get us all started, I have a very simple question, which is to do with a very basic principle of probability, and then we will define the terms and we'll see what it is. So the question is this: suppose you toss two coins in the air. So probability, usually the kind of problems that I love in probability either involve coins, or involve dice, or involve cards, or sometimes all three of them. Okay, so we are going to start about a very interesting problem on coins. So let's see what happens. The question is this: suppose you toss two coins in the air and they fall down, and you leave the room. Okay, you leave the room and you don't know anything about the coin. Somebody else enters the room and looks at the coin and then tells you, hey, one of the two coins that you tossed landed as a tail. One of the two coins. Okay, the question is, what is the probability that the other coin is also a tail? So let me repeat. You throw the two coins in the air and you leave the room, and somebody else comes into the room and looks at the two coins and then tells you that one of the two coins which you tossed has fallen as a tail. And then the question is, what is the probability that the other coin is also a tail? So I will allow you to think over that question, and I am going to start defining a few basic terminologies, and we will see how to approach this problem in a very nice way where we're not confused. So I'm already having some answers, and some of them are wrong, some of them are right, and let's see what happens. Okay, so this is done. These are all the odd number factors, which are the square numbers. Okay, so the first thing that we have to understand in probability is it is a complete study of data which is given to us. and it also, some sort of it makes predictions based on all possibilities. Okay, so what I'm going to type is events, outcomes, chance. These are the three things that completely decide the field of probability, and you're all very much aware of all these three things. So an event is something which happens, and then an outcome is the different ways in which that event can happen, and then we study the chance. The total chance of an event happening is when I talk about total chance, this is a very English term. Let me define it mathematically. What I'm trying to say is, when an event happens, before it's happening, and we want to look at all the different ways in which the event can happen, like we study all the different outcomes, the probability that the event is happening is 100. The discussion is only about the different outcomes. Like, for example, in the case of somebody winning a match, the fact that somebody wins a match is certain. It has to be 100%. There is a result. Let me make it more clear. Let's say there's a result, and that's 100%. And now the study is only about whether it is this team that has won or the other team that has won, or if there's a tie. But if you add up all those three probabilities, it has to add up to 100%. So if we say that there's a cricket match happening between South Africa and Australia, we say that there's a 40% chance that South Africa wins the game. There's a 50% chance that Australia wins the game, and there's a 10% chance that there's rain. Okay, or let's say there's 9% chance of rain and 1% chance of it being a tie. So if you add all of them, it has to be 100%, because there's nothing else which can happen other than these outcomes. So event is just the totality of all those outcomes. One of those outcomes has to happen. We cannot say that none of those outcomes happen. Okay, so that's one thing. The other thing is, we discuss the chance of an outcome. So how do we do this? We say which are all the possible outcomes, then we say which is the outcome that we want, and then we say, okay, we want this one out of all that, so what is the chance of that happening? So we put one of them in the numerator and then everything else in the denominator, and that's basically it. There's nothing more. It's just a variation of these simple facts that creates this entire field of mathematics. So for example, when we talk about a simple card experiment, you say that from a deck of 52 cards, if you pick a card, what is the chance that it's going to be an ace? So you're picking a card, that's an event, so the card has to be something. And now you say, what is the chance that it's an ace? So you first think about how many ace cards there are in an entire deck, and there's one for each shape. So there are 4 ace cards, and then there are total of 52 cards, which means the chance of it being an ace is 1 by 13. So this is pretty straightforward, right? If there were 6 ace cards in that pile, we would say 6 by 52. If there was only 1 ace card in that pile, we would say 1 by 52. If there were no ace cards, we would say the chance of getting an ace is 0. If all of them were ace cards, then the chance of getting it is 1. So this probability is sometimes 100% or sometimes 1. It's the same thing, and it's based on the context. Sometimes you say 1, sometimes you say 100. So usually you talk about 1 when you deal in fractions. If I want to say 1 by 5, 10 by 13, or things like that, then we talk about 1, because the one fraction is complete. But when you talk in day-to-day life, what is the chance of it raining? You don't say 9 by 10, you say 90%, because intuitively, when we talk about things like 100%, 50%, 0%, we kind of understand it better than somebody saying, hey, there's a 7 by 13 chance that it rains. So that doesn't really tell us a lot of data. But instead, if they said that there's a 55% chance of rain, then that's a lot more clear. So that's it. The total of everything adds up to 1. And so now from that, we can understand one thing, that if we are talking about an event A which is happening, let's say an event A has chance 45%, just a random example that I'm giving, then the chance of event A not happening will be 55%, because I'm using the word chance just to give it a more intuitive feel, it's actually the word is probability. So if you say that there's an event A which is happening and the chance or the probability of that event happening is 45%, then the probability that that event does not happen is 55%, because we said that everything has to add up to 100. So if that event happening is 45, then the event not happening is 55. We don't care about how many other events might happen. It's just that this event is not happening. Remember logic, right? Not of A. So it's just not of A plus A should be the full probability. There's nothing else that can happen, right? You take any event, take any outcome, then there are only two possibilities. Either the outcome happens or the outcome doesn't happen. There's nothing else which is possible. So if you say, any team is playing a cricket match, either it wins or it does not win. Remember, I'm not saying whether it wins or loses, because lose is also a different outcome. I'm just saying whether it wins or does not win. There are only two things possible. You can either win a game or you don't win a game. Now, when you don't win a game, it could be that you lost the game. It could be that the game didn't happen because of rain. It could be that the game was tied. It could be anything. But the fact is that you did not win. Okay, so now coming back to that problem which I asked, a lot of people have sent me different answers. I have some answers which are half. I have some answers which are 1/4. And I have an answer which is 2/3. And I have an answer which is 1/3. And I have an answer which is 25%. So that's almost the all possible logical answers for that question, because nobody will say 1/7, or nobody's going to say 11%, right? So there are only 4 things which you can think of. Either it is half or 1/3 or 2/3 or maybe 3/4 or 1/4, like maybe 5 things. That's it. So when we do this probability, this coin problem solving, let's take the help of one of the tools that we used when we talked about logic, that's truth table. Now we're not going to actually do a truth table, but we're going to do something similar. So let's say 2 coins are tossed, coin A and coin B. Now what are the different ways in which these 2 coins can fall? Coin A can either be a head or a tail. That's all it can be. And coin B can also be a head or a tail. So when coin A is a head, coin B could be a head. Or we could have coin A as a head, and then we could have coin B as a tail. Or we could have coin A as a tail, and then coin B is a head. Or we have coin A as a tail, and we have coin B is a tail. Now, suppose we know that coin A is a tail. What is the chance that coin B is a tail? 50%, because we know that coin A is a tail. So once it's a tail, there are only 2 possibilities. Either this is a head or a tail, so it's 50%. Now, suppose we know that coin B is a tail, then what happens? If coin B is a tail, there are 2 possibilities, where either this one or it's this one. So then the possibility that coin A is a tail should also be 50%. Now let me confuse you a little bit. So the probability that coin B is a tail, suppose coin A is a tail, is 50%. The probability that coin A is a tail, if coin B is a tail, is also 50%. So then we don't care which coin it is. If one of them is a tail, the fact that the other one is a tail is 50%, because whichever the coin is, we didn't know whether it's a head or a tail. The other coin being a head is the other coin being a tail is 50%. Or maybe it should be that there's 50% chance that this happens, there's 50% chance that that happens. So then it has to be 50 plus 50 divided by 2, which is 25%. How many of you feel that the first justification that I gave actually makes sense? So let me repeat myself. If coin A is a tail, then the possibility that coin B is a tail is 50%, because we eliminate these 2 options completely, because we know that coin A is a tail. It has to only be one of these 2. So the chance of coin B being a tail is 50%. So do we agree? If coin A is a tail, the chance of coin B being a tail is 50%. This is pretty straightforward, and I didn't cheat anything. I'm just telling the fact. Now let's do the other thing. If coin B is a tail, the chance that coin A is also a tail is 50%. Right? There's absolutely nothing, because if coin B is a tail, then it eliminates the first and the third outcome. So it has to be one of the second or the fourth. So it has to be the fourth. So it's 1 out of 2. One question I want to ask you is, does anybody feel that there is another outcome possible which has not been listed on this table? If you do, just type it in the chat. We have 2 coins which are being tossed, and I've just listed down the different ways in which they can fall. I feel that the coin A can either be a head or a tail, and coin B can also be a head or a tail. So we just have a head, 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 tail, tail, head, tail, tail. Now, maybe in an ideal world, there is a 1 by, I don't know, million chance that the coin can actually fall exactly in the middle. But we are going to ignore that, because I think that probability is too small for us to, care about. It's just negligible. So we are only thinking about a coin which will only fall either ways. So let's think that this is a computerized coin. Oh, but no, it's not a computerized coin. We created a story where it's tossed in a room. So let's stick with the story, but let's say that actually both of the coins fell properly. They didn't stand in the middle. They didn't bump into some chair, nothing. Does anybody feel that there is any outcome which has been ignored in this particular event? Is there something else which can happen? No. Okay, so now there are 2 possibilities. If coin A is a tail, then the chance of coin B being a tail is 50. If coin B is a tail, then the chance of coin A is also being a tail, 50. So now we know that one of them is a tail. Thus, the chance of the other being a tail is 50%. How many of you are convinced by this argument? Just raise your hand if you feel that this argument is good. Just raise your hand so that I can keep a count. Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to wait for some time. I'll wait for everybody to raise their hands. Whoever feels this is correct. Okay, so that is about 14 or 15. Oh, one. Okay, there's still more people raising their hand. People have probably, some of them have not yet figured out where to press the button, because I don't want you to type. Okay, so okay, this is about half of the class. Okay, now I'm going to give you another justification, and let's see how many of you agree with this one. You can agree with both. So I don't have any rule that you have to agree with only one, because remember, we are only talking about an event happening, and we're talking about a probability of an event. So we are outside the room, and somebody has looked at a coin and they have told us one of those is a tail. What is the chance? So whatever we discuss, or how much ever we agree upon something, it's not going to change what actually happened, because the other coin actually will either be a tail or a head. The chance might be high or low, but there's only one thing that can happen. Just because the chance of it being a tail is high, it doesn't mean it's a tail, right? So we're just trying to analyze. So you can actually be convinced by 2 arguments. Now let's go with another argument. I say that if coin A is a tail, the chance of coin B being a tail is 50. If coin B is a tail, the chance that coin A is a tail is 50. So now we don't know which of them. Therefore, it is going to be 50 plus 50 divided by 2. So the chance is going to be 25%. How many of you agree with this argument? Raise your hands. The other ones can put your hand down. The ones who raised the hand for the first one, put your hands down and keep it only if you feel that this argument makes sense. That one of them, it's 50. The other one, it's 50. Now we don't know which one. So we have to take the average of both those events, and we end up with 25. Okay, so we have about 9 or 10 people who have raised their hands. As you figure it out, I want to give you one more justification for 25%. We have 4 possible options. One is head, 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 tail, tail, head, and tail, tail. And now somebody has told us that one coin is a tail, and now we are asking what is the chance that the other one is a tail. So if the other coin is also a tail, then what does it mean? It means that both the coins are tails, right? One of them is a tail, which has been told to us, and now we are trying to guess that the other one should also be a tail. So we are technically trying to find the event where both those coins are tails. And out of those 4 events, only one event has both tails, which means the chance of that event happening should be 25%. How many of you agree with this logic? Like, keep your hand up. Whoever agrees with that logic of 25%, keep your hand up. That there are 4 events: head, 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 tail, tail, head, tail, tail. Whatever event we want now requires both the coins to be tails, because one of them is a tail, and now we are seeing that the other one should also be a tail. So the chance of that event happening is 1/4. Okay, nice. So we have about 10 people. Okay. My last thing that I want to say is the answer is not 50%, the answer is not 25%, it's something else. How many of you feel it's something else? Raise your hand. It's not 50, not 25. Both the things which I said are wrong. There's something else which I have not spoken about, which you feel is correct. Then you raise your hand. Very interesting. Okay, so we have a very almost divided class, because we had about 12 people who agreed on 25%. We had about 16 people who agreed on 50%, and now we have about 10 or 11 people who said there's something else. Okay, so let me reveal the actual answer, and I don't know how many of you would be a little surprised by this one. The actual answer is 33%. It's 1 by 3, which is 33%. So I will justify this, and then we will talk about probability in a different way, because this is a very non-intuitive situation, but I think it clarifies a lot of things on probability, which will tell us the most important thing is that in probability, sometimes our intuition can be wrong. Let me tell you my intuition when I first saw this problem. I don't care about this formula. I don't care about the table which I did. I don't care about which one is a head, which one is a tail, or all that complications. I'm only thinking, okay, one coin is a tail. I don't care about it. Now they're asking me about the other coin. They're saying, what is the chance that it's a tail? Well, it's a coin. It went up in the air and it fell down. What is the chance it's a tail? It's 50%. How does it matter what his friend or his neighbor or another coin in India or some other coin in some other galaxy? How do we care about that? We are looking at one coin. Somebody asked me, what is the chance that the other coin is a tail? Well, the other coin was tossed. It went up in the air and it fell. So the chance that it's a head or a tail should be 50%. Why do we care about 2 coins being tossed, me going out of the room, somebody else looking at one coin, and saying that one of those is, I mean, how does that matter? There was one coin. We are asking whether it's a head or a tail, so it has to be 50%. But unfortunately, probability doesn't work that way, because we did not specify which coin. We just said the other coin. And although in English we can say that the other coin has to be one coin which went up in the air and fell, mathematically that other coin could be both of them at the same time. Let me repeat. The other coin we think is actually only one coin, because we say, oh, there was one coin. What is the chance it's a tail? It's 50. But in reality, because we don't know which of those coins is a tail, we have to calculate the probability for both of them and add them up. If that doesn't make sense, let me go back to my table. So the reason why I did this table is to actually explain this in a more believable manner. We know one thing for sure. Now, this thing can be said even by the people who said 25, even by those who said 50, even by those who said 33, or even by those who did not vote at all. We can all agree on one thing, that the first option is not possible. The one that I have just clicked on, the head option, is impossible, because our friend has told us that one coin is a tail. He didn't tell us which one, but we know that one coin is a tail, which means the first option is completely impossible. We cannot have both the coins as a head. Now, the second option is possible, the third option is possible, and the fourth option is also possible. So the only thing that we know is that the first option is not possible. So I'm just going to erase that. Now we have three options remaining. So now you kind of know why it's 33%, because it's 1 by 3. So it's actually 33.33%. Now we have three possibilities. And we have been told that one of the coins is a tail. What is the chance that the other coin is also a tail? And out of the three possibilities, there's only one possibility where the other coin is a tail, which means both of them should be a tail. So I had given a justification, remember, just about 5 minutes back, and I said there are 4 outcomes, and the outcome that we are seeking is the one where both are tails, so it should be 1 by 4. But it's not 1 by 4 because the first outcome is not an outcome anymore. It existed before the coins were tossed, but we have information which says that one of the coins is a tail, which eliminates one of those outcomes completely. Like, for example, if before the cricket match, the same example, we said that there is a chance of South Africa winning, there's a chance of Australia winning, there's a chance of a tie, and there's a chance of a rain. Suppose a match is already over and it's done, and we know that somebody won, but we don't know who, then the rain and the tie are automatically gone. They are not possible outcomes anymore. Okay, so we only have to think about, did South Africa win, did Australia win? We cannot even think about the rain or the tie because we know that that didn't happen. So that is gone out of the denominator. So we cannot do 1 by 4 because the 1 by 4 assumes that there are 4 possibilities. Well, there were 4 possibilities initially, but because we have some information that one of the coins is a tail, it eliminates one of those 4, leaving us with 3 possibilities only. So out of those 3 possibilities, there's only one way where both of them can be tails. So it's 1 by 3. Extremely counterintuitive, but that's how it is. So this is called dependent probability. It's also called conditional probability, where what is happening is, it's not just that that event has happened. You have some extra information on that event, which you will have to factor into before you predict. So if now somebody said that there's a chance of head and head happening is 25%, we would call them a fool because the head and head cannot happen because one of those coins is a tail. Now, why is it important that this person walks out of the room? And why is it important that we say that one of the 2 coins? Because if somebody had said that the first coin is a tail, or if somebody had said that this coin is a tail, then automatically that coin is out of the equation because we know its identity. We only look at the other coin, and my previous justification of saying, I don't care what has happened, I just look at one coin and I say whether it's a head or a tail, that comes into the picture. Because then you're only talking about one. But then if you say one of the 2, then you're talking about many. So that is how it works. And now let us try to solve some problems. Let's try to do a very interesting card problem, and let's see what to do. Okay, I have a question for all of you. If I randomly pick a card from a deck, so when I say a deck, it's 52 cards, and we don't talk about jokers here, and it's a well shuffled deck, and there's no tricks here. If I randomly pick a card from a deck, what is the chance that it is a red prime? Can all of you just quickly solve this? This is not too hard. It's pretty basic. Just it's just listing the total outcomes and then dividing by the event. Yeah, you don't have to type the answer. You can just solve it. There's a red prime, so keep that in mind. Okay, so maybe most of you have solved it, and I will talk about how this was to be done. Oh, somebody's asking if king and jack come in primes. No. We are only talking about 2 3, 5, and 7. We're not going to be, we're not giving numbers to 11 and 13. That's a good question. That's a valid question, but okay. So the first thing that we have to check is how many red primes there are, which is not too hard because there's 2, 3, 5, 7. So there are 4 primes per shape, and there are 2 red shapes, so it's 8. So it's 8 by 52, which is just 2 by 13. Right? So this is one of those examples where you just have to do the desired event divided by the total. Now let's make it a little bit interesting. Suppose I draw, or let me type it so that, but sometimes I feel when I tell it, you understand it better because I'm stressing on the important things. Suppose I pick a red prime from a deck. Suppose I pick a red prime from a deck. Okay. And I put the card back. Pay very close attention. Suppose I pick a red prime from a deck and I put the card back. What is the chance that I pick a red prime again? Suppose I pick a red prime and I put it back. What is the chance that I pick a red prime again? So just type your, don't type your answers in the everyone chat, just message it to me privately if you get it. Let's see. Okay. Getting some very interesting answers. I say that because I have 2 answers which are different from each other. So that's what makes it interesting. I got another answer. Okay. When I say another answer, I don't mean another message. I mean a different answer. And all of you are smart people. So when you give me different answers, it makes me excited because then I actually get to justify why that answer was wrong or correct. Okay. Very nice. Very nice. Okay. So the word again here is very important. So you pick a red prime from the deck, you put it back, and then you pick a card, and then you say, what is the chance that it's a red prime again? Well, some of you have done some multiplication, and you have done 2 by 13 multiplied by 2 by 13 because you're saying that the event has to happen again. So you're saying 4 by 169. So let me write that here. And for this answer, you get 7 out of 10 points for thinking of that answer, because I have not yet told you about the multiplication of probabilities, but you actually thought about it. So that's a good idea. Somebody typed 11 by 13. I don't know why that's true, but let's just write it here. And then people have said 2 by 13, and somebody has said past doesn't matter. There's a little bit of philosophy there. The past doesn't matter. It's actually true. So this was a trick question. And if you paid close attention, you would understand that I said that you have already picked a red prime. I didn't ask you what is the chance that you pick a red prime, put it back, and you pick it again. Then it would be 4 by 169. But I said you have already picked a red prime. Now you put it back. Now what is the chance that you pick a red prime? The thing about probability, which is extremely non-intuitive, is that even if you conduct 1 trillion experiments, okay, when you do the 1 trillion and first experiment, you again have the same possible outcomes and the event. If I toss a coin 50,000 trillion billion times, and every time it's a head, the chance of that happening is actually 1 by 2 to the power whatever number I told. But let's assume that I got so many consecutive heads. When I toss the coin for the next time, there's again half a chance that I get a tail. It doesn't matter what I did in my previous. So this actually is, I actually thought of this once when I had actually read a puzzle. And sometimes when you talk about these things, like, lightning doesn't strike the same place twice, or you talk about if you have been involved in a plane crash, you will never be involved in a plane crash again. Or you say that if you failed in one exam, then next time you will do well. So these are all things which are told in our day-to-day life, but they don't make sense probabilistically. Let me tell you why. there's a question that there's a very famous proverb that says that lightning doesn't strike the same place twice. And what it means is that if at all lightning struck a place, then that place will never have lightning again, because what is the chance that the lightning will strike the same place twice when there are, I don't know, 200 countries each having millions of cities, right? But probability says that once the lightning has struck the city, then the lightning doesn't care about where it has struck or not. Again, it picks randomly which city to strike. Now, if in the beginning of 2000, when the 2000 century began, if you say what is the chance that San Francisco will be hit by lightning twice, then the chance is very low, because the same, I don't know how lightning can strike the same place twice. But suppose, let us say that San Francisco has already been struck by lightning, and now you say which city has a higher chance of being struck by lightning? Is it San Francisco or is it Mumbai? Then it's going to be the same thing, because once an event has happened, it is gone, it's forgotten. We cannot assume that, oh, because it happened before, it won't happen again. So that's the same logic here. You might have been extremely lucky and you picked a red prime, but when you pick a card again, the probability rules all forget what happened and they come back to following the same principle of desired event divided by the total event. It doesn't care about how many times you've done it. So let me tell you this, if somebody has won the lottery, then when they compete again, they have the same chance of winning the lottery again. So this can be easily understood when we talk about the boy-girl scenario, when a couple is having a child. So I will list down the 3 questions. The first question is, what is the probability that their first child, so there is some couple, John and Mary, whatever, their first child is a boy. Okay. What is the probability that their second child is a boy? Remember, every time you answer a new question, you have to answer it assuming that the previous questions didn't exist, right? So we're talking about from the beginning. Think that all these questions were asked on the day of their marriage. Okay, these questions are asked on the day of their marriage. So nothing has happened yet. We're just trying to guess. What is the probability that both their kids are boys? What is the probability that one of their kids is a boy? And now the 5th question is actually not asked on the day of the marriage, it's asked a little bit later. They had their firstborn, let's say their firstborn was a girl. What is the probability that their second-born is a girl, is also a girl? And the last one, which is the exact same question of the coin toss problem, which we first did, 25 years later, we meet the couple and they tell us that one of their kids is a girl. What is the chance that the other kid is also a girl? Now, this is not exactly the same as the coin toss thing, because this is different. It's actually involving events that have happened, and this is talking about children being born. So don't directly apply the logic. There's a little bit of difference, but let us see if anything at all holds from whatever we've discussed so far. And we can take a break from today's session once we discuss these 6 possibilities, and then we can stop. So let's just now think about all the 6 scenarios. I don't want anybody to type any answers. I will let's just discuss this, because this is very interesting. So the first thing is pretty straightforward. What is the probability that their first child is a boy? This is half. I don't think anyone will have any confusion here. What is the probability that their second child is a boy? Now this is a little confusing, but because we have discussed all this, I think you know that that is also going to be half. It is going to be half because we don't really care about what happened in the first child or anything. We just say, what is the chance that the second child is a boy? It's still going to be half. What is the probability that both their kids are boys? Now this is 1/4 because we are asking this before both of them are born. So then we want the first one to be a boy and the second one also should be a boy. So it's 1/2 times 1/2, which is what some of you did for the red prime problem. It is, one thing has happened and the other thing also should happen. So you have to assume from the situation before the first event has happened. So you have to actually multiply both of them. It's going to be 1/4. What is the probability that one of their kids is a boy? This is something that we have not yet discussed. This is to do with this truth table here, which we had done. Not the truth table, the event table. I don't know. I think I erased it. But what it means is that we don't care if it's the first one or the second one. What is the probability that one of those two is a boy? So then it's easy to think about this from that logic, which I talked about in the beginning of the class, where I said that if an event is happening, then the chance of that event not happening is 100% minus that, or 1 minus that. So which is the event that should happen so that none of them will be boys? There's a fourth question. The fourth question is trying to find out what is the probability that one of them is a boy. So what is the event that should happen such that both of them are not boys? The event is that both of them should be girls. That is the only event which will make the fourth question wrong, meaning it will make the fourth question not possible. So the event where the fourth question can fail is if both of them are girls. Because if both of them are not girls, we don't care if both are boys or one is a boy, then the fourth question's conditions are satisfied. So now what is the chance that both of them are girls? That is simple, it's 1/4. So what is the probability that one of them is a boy? It has to be 1 minus 1/4, which is 3/4. There's a 3/4 of a chance that if there are two kids, one of them is a boy. Little non-intuitive, but we are not saying which one. It could be the first boy or the second one or both of them. Now the fifth one, the firstborn was a girl. What is the probability that the second-born is also a girl? This is a little similar to the last question that we discussed with the red prime, where we said that the past doesn't matter. That's the same thing here. It is still 1/2. Because the firstborn was a girl, is already happened. She's born. Before she was born, there was a chance, there was a discussion. We don't know if she was a boy or girl, but she's born. And now the laws of probability go back to their normal root, the normal origin, whatever that is. And when the next child is conceived, there's still a 50% chance. It doesn't matter what happened in the past. And let's say the second child is also a girl, and now when the third child is born, again it's a 50% chance that it's a girl. But if you ask the same question before any of those kids were born, then the chance of all the three being a girl is 1/2 times 1/2 times 1/2, which is 1/8. So if it looks a little counterintuitive, let me tell you this. What was the probability that when Usain Bolt was born, so when he was born, he's just born, okay, we don't know anything about him. What was the possibility when he was born that this guy will win all the 9 gold medals in all the 300 meters, all the 200 meters, and all the 3 relay races in 2008, in 2012 Olympics, and the 2016 Olympics, and he will be the fastest man on earth, and he will run 100 meters in less than 10 seconds, on less than 9 point whatever seconds? The chance of that happening was really, really, really small. In fact, the chance of that happening was almost the same as when I was born, or when any of you were born, or when Usain Bolt was born. The chance is the same because we're all just born. So this probability is, let's actually say it's 1/billion. Because there are 7 billion people, let us say there are 7 of them who will probably be that fast. So it's 7/7 billion, which is 1/billion. Now let's fast forward a little bit. Let's say now Usain Bolt is 10 years old, and he's the fastest kid in his school. Now, what is the possibility that he actually goes on to do all the things? And that's going to be 1 by a million. I don't know why this is falling off. Just a second. That's going to be not 1 by billion, but that's going to be 1 by million, because now we have information that this guy is the fastest kid in his school. So then we can ignore those people who were not the fastest kids in the school. So now the sample set has reduced a little bit. So it's 1 by a million. Now let's fast forward by 10 more years. Let's say now he's the fastest 18-year-old, or he becomes the fastest guy in his high school, this thing. It becomes probably 1 by 100,000. Then we say he wins the 2008 Olympics. Then it becomes 1 by 1,000. Then we say he also wins the 2012 Olympics. Then it becomes 1 by 10 because there are only 10 people in the final race. And then he also wins it, so it becomes 1. So as his life goes on, he creates events that make the possibility more and more likely. So the same thing happens here. It's 1 by 2. Now let's say 25 years later, we meet the couple and they tell us that one of their kids is a girl. We don't know which one. What is the chance that the other is a girl? Although I told you that it's different, it's actually not different. It's still 1 by 3. It's the same logic of the coins. But here it is so counterintuitive, because you say that, okay, we don't care which is the girl, because you say that one of them is a girl. The other one could either be a boy or a girl. So it's only 50%. How is it 1 by 3? Well, it's because we don't know if it's the older one or the younger one who is a girl. So it can happen either ways, right? It could be the older one or the younger one. So you have to consider both those possibilities. And eventually you go by the same logic that we did for the coins, and it's 1 by 3. Okay, so this was a very, I think, nice session, and I really enjoyed talking about all these things. Please ask me any questions if you do have, and we will continue talking about this, and we'll solve some more problems in the next class. So does anybody have any questions?